This is paper 6, Calculus of Several Variables. Right now, we are in the first chapter, Functions on Rn. In the earlier module, we discussed what do we mean by the symbol Rn, some basic properties from linear algebra and some notions from topology. Right now, we shall discuss scalar and vector fields in this second module. After going through this module, we shall be able to know what do we mean by scalar and vector fields on Rn. Then we shall study vector valued functions of a single variable and calculus on them. And finally, we shall study applications of such functions in geometry. We start with two concepts from linear algebra, basis and frame. We start with basis. Let V be a vector space over R. By a basis of V, we mean a collection of vectors S from V such that every vector in V can be uniquely expressed as a linear combination of members from S. This is equivalent to say that the collection S is both linearly independent in V as well as it is a spanning set for V. Clearly, a basis of a linear space is not unique. As for example, if we consider the vector space R over R, then any non-zero real number constitutes a basis for this. Now, we come to frame. By a frame, we mean an ordered basis. While dealing with the linear space Rn over R, we shall frequently use the frame E1, E2 up to En. Here Ei is the ith unit coordinate vector, which has the ith component 1 and all other components are 0. Now, we go to scalar and vector fields. We shall classify functions depending on the dimensions of domain and codomain space, that is on M and N. So, we are dealing functions from subsets of Rn to Rm. If both n and m are 1, then such a function is a real valued function of a single real variable. We studied them in any course in real analysis, and we shall frequently recall the concepts and use them to study. Secondly, if n is greater than 1 and m is 1, that means the dimension of the domain space is greater than 1, but that of the codomain is 1, then such a function is called a real valued function of a vector variable. Thirdly, if n is equal to 1 and m greater than 1, that is domain is a subset of R, but codomain is Rm where m greater than 1, then such a function is called a vector valued function of a single real variable. We shall start our study with this kind of functions. Final one, when both n and m are greater than 1, that means dimensions of both the domain space and the codomain space are greater than 1, then such functions are called vector valued functions of a vector variable. Let us now discuss what do we mean by component functions of a vector field. Let S be a non-empty set in Rn and F is a map from S to Rm. Corresponding to each x in the domain set S, there is unique y equal to f x in Rm. Now, y is a member of Rm, so we can express it as a m tuple of real numbers y1, y2 up to ym. Now, if I look at any of this, say y1, if I change x, it will change, if I change f, it will change. So, these many real numbers depend on both the point x as well as the function f. Moreover, this yi is defined real valued functions on the set S. As all these functions are derived from f and are associated with a particular component I, we prefer the notations yi equal to f I x for each x in S and for each I running from 1 to m. So, we have defined m many functions from f1, f2 up to fm, all of which have domain S and codomain R. We call them component functions of f. We shall use a notation f equal to ordered m tuple f1, f2 up to fm. Now, how to find one particular such component? If I take inner product of f x with the ith unit coordinate vector, it will give me the ith component. Now, let f and g be two functions defined on a set S, where S is a subset of R and their codomain is Rm, and let alpha be any scalar. We can define sum of two functions f plus g and a scalar multiple alpha f, where alpha is any scalar, from S to Rm using pointwise principle. That is, for each x in S, we define f plus g over x gives me f x plus g x, and alpha f acting over x gives me alpha times f x. We can easily check that the components of f plus g are components of f added with components of g. That means, we can write f plus g as the m tuple f1 plus g1, f2 plus g2 up to fm plus gm, and alpha f equal to alpha f1, alpha f2 up to alpha fm, where f and g have components f1, f2 up to fm and g1, g2 up to gm respectively. In a similar fashion, we can define the inner product of two functions. Let f and g be two functions from S to Rm. So, f x and g x both are members in Rm. We define inner product f g acting over some point x in S by inner product f x and g x. So, in short, we can write inner product of f g equal to f1 g1 plus f2 g2 plus up to fm gm. Now, we shall enter into the study of calculus. We know any study of calculus starts from the study of limit. So, we shall start with limit, and after that with itself we shall study continuity and differentiability. Now, we start with the limit of a vector valued function of a single variable. Let f be a map from S to Rm, where S is a subset of R and f is defined in some deleted neighborhood of a point A. Then the limit of f as x approaches A is defined as limit of f x as x tends to A is the m tuple, first one limit of f1s as x tends to A, second one limit of f2x as x tends to A, and so on. From our study in calculus of one variable, we know from Hausdorff property it follows that limit of a function is unique. So, if we look at the component functions f1, f2, fm, all these are real valued functions of a single real variable. So, their limits, if exist, are unique. So, it is obvious that the limit of f x at x approaches A is also a unique element in Rm. Now, let limit of f I x as x approaches A is b I and b equal to b1, b2, bm. Then we can easily check from the definition limit of f x as x approaches A equal to b if and only if for each I limit of f I x equal to b I as x approaches A. Equivalently, for each I limit of f I x minus b I should be 0 as x approaches A. Equivalently, limit x approaches A, modulus of f I x minus b I should be 0. That is, if and only if as mod of x minus A approaches 0 plus mod of f I x minus b I should approach 0 from the right. That is, if and only if norm of f x minus b approaches 0 from the right as mod of x minus a approaches 0 from the right. That is, limit of norm of f x minus b as mod of x minus a approaches 0 plus should be 0. The importance of this calculation is that if I look at the first step, there I have limit of a function of several variables, but if I look at the last part, it gives me a function of a single real variable and it is real valued, because we know norm of f x minus b is a real valued function. That means we can study calculus of several variables with the help of calculus of one variable as far as limit is concerned. Now, the basic components of calculus can be extended to vector valued functions in a component wise fashion. From the definition of limit, two results follow instantly. First one is limit of f plus g at the point x as x approaches a equals with limit of f x as x approaches a added with limit of g x as x approaches a. That means limit of sum equals with sum of limits. Secondly, limit of the function alpha f as x approaches a is equal to alpha times limit of f as x approaches a. We have similar result whenever we consider the inner product of the functions f and g. Limit of extending to a inner product of f g x equals with inner product of limit of f x as x tends to a and limit of g x as x approaches a. In the above, we assumed that all the limits under consideration exist finitely. After limit, right now we are in a position to discuss continuity. The continuity of a vector valued function at one interior point of its domain can be defined as was done in case of real valued functions of a single real variable. Let f be a function defined over a set S, which is a subset of reals and its codomain is R m, and let A be an interior point of the set S. Then f is said to be continuous at the point A if and only if limit of f x is f a as x approaches A. From the above definition, we conclude that a function f from S to R m is continuous at a point A if and only if all its component functions f 1, f 2 up to f m are continuous at the point A. Thus, it is clear that if two functions f and g from S to R m are continuous at an interior point of its domain, say A, then the sum function f plus g is also continuous at the point A. For any real number alpha, the function alpha f is also continuous at the point A. The function inner product f g, it is a real valued function of a single real variable, it is also continuous at the point A. Now, we are going to introduce the concept of differentiability. Whenever we are introducing the notion of derivative, we should be very careful that it should imply continuity as well as it should satisfy linearity properties and Leibniz property. Let f be a map from S to R m, where S is a subset of the reals and A is an interior point of S. Let us give an increment h to the independent variable A. So, the corresponding change in the dependent variable is f of a plus h minus f a. Now, f is a map from S to R m. So, f of a plus h as well as f a both are members of R m. So, their differences also. We consider a scalar multiple of this vector by the scalar 1 by h and then consider the limit as h approaches 0. If this limit exists finitely, we call it the derivative of f at the point A and in this case we say the function is differentiable at the point A. Now, we are going to use the definition of limit to find a simplified version for f dash A. We are finding the limit of f of a plus h minus f a by h as h approaches 0. So, let us first write down f of a plus h and f a in terms of their components. So, what we have f 1 a plus h minus f 1 a by h up to f m a plus h minus f m a by h. We calculate the limit of this vector as limit as h approaches 0. So, finally, what we have the m tuple f 1 dash a up to f m dash a. Here we have assumed that all the limits exist finitely. From this, we conclude that a vector valued function is differentiable at an interior point of its domain if and only if all its component functions are differentiable at that particular point. Now, we shall study the linearity properties of derivative. We consider two functions f and g from S to R m and let a be an interior point of the domain set S and alpha be any real number. First, we assume that both the functions f and g are differentiable at the point A and their components are f 1 f 2 up to f m and g 1 g 2 up to g m respectively. We are going to first find the derivative of the function f plus g at the point A. We know the derivative of f plus g will be the m tuple comprising of derivatives of its component. So, the first one would be the derivative of the first component of f plus g. So, it is nothing but f 1 dash plus g 1 dash at the point A. So, finally, what we have the derivative of f plus g at the point A equals with f dash a plus g dash a. That means, derivative of sum equals with sum of derivatives. Now, we consider the function alpha f. We are trying to find out the derivative of the function alpha f at the point A. So, its derivative would be the m tuple whose first one would be the derivative of the first component of alpha f, that is alpha f 1 dash at the point A. So, what you finally get that the derivative of alpha f at the point A is alpha times f dash a. After linearity, it is now time to check the Leibniz properties. We assume another function u which is defined on S and is real valued, and we are trying to find out the derivative of the function u f at the point A. We can easily check from these calculations that the derivative of u f at the point A equals with u dash a f a plus u a f dash a. If we look at the last line, u dash a is a real number, f a is a member of R m. u a is a real number, f dash a is a member of R m. So, we have a element in R m. We are continuing with Leibniz properties. Now, we shall consider two vector valued functions. Let f and g be two maps from S to R m. Both of them are differentiable at a point A interior to the set S, and we are trying to find out the derivative of the inner product f and g. Here we notice that inner product of f g is a map from S to R. We have shown the calculations here. We can easily check the derivative of the function inner product f g at the point A equals with the inner product of the functions f dash and g at the point A added with the inner product of the functions f and g dash at the point A. So, we can say that derivative of inner product f g equals with inner product of f dash and g added with inner product of f and g dash. Finally, we are going to state the zero derivative theorem. First, we recall that an interval in R is a connected set. Let S be an open interval and f from S to Rm be differentiable at each point of S. We further assume that at each point of the set S, f dash a is the 0 vector of Rm. We are going to show that f is a constant map on S. What we have? For each a in the set S, f dash a equal to the 0 vector implies that all its components must be equal with the real number 0. So, there exist m many real constants C 1, C 2 up to C m such that f I a equals with C I. So, what we have? F a equal with the ordered m tuple C 1, C 2 up to C m, say C. We should be very careful. The above result may not be valid if we replace an open interval by an arbitrary and open set, because connectedness plays a crucial role here. Now, we are going to discuss some applications of whatever we have studied. We are going to discuss its applications in differential geometry. Now, we are going to study differential geometry of curves. By a curve in Rm, we shall mean a continuous map from an interval to Rm. Let I be an interval and gamma from I to Rm be a continuous map. We know an interval means a connected set in the real line and continuous image of a connected set is connected. Hence, it follows that the set gamma I is a connected set in Rm. The set gamma I will be called the trace of the curve gamma and the elements of the interval I will be called parameters. Here we shall consider only non-constant maps gamma from I to Rm. Otherwise, gamma I is a singleton set, that means a single point in Rm. Right now, we give some examples of curves. Let us consider the map gamma from I to R2 defined by gamma t equal to Pt plus q, where P and q are vectors in R2 with P non-zero and I is an interval. If P equal to P1, P2 and q has the components q1, q2, then we can easily check gamma 1 t will be P1 t plus q1 and gamma 2 t will be P2 t plus q2. We can find that gamma denotes a straight line segment, and if we take I equal to R, it will give a straight line which pass through the point q and is parallel to the vector P. Another example, we consider the map gamma from closed interval 0 to 2 pi to R2 defined by gamma t equal to R cos t R sin t, where R is greater than 0. Then gamma denotes the circle in R2 of radius r with center at the origin. Now, we discuss what do we mean by tangent to a curve. Let gamma be a map from I to R2. Let t be an interior point in I. We choose some h such that t plus h is also in I. Since t is an interior point of the set I, we can always find some h. Now, gamma of t plus h and gamma t both are members in Rm, so their difference is properly defined. We consider the vector 1 by h gamma t plus h minus gamma t. If we look at the figure, we can easily find gamma of t plus h minus gamma t is the chord joining the points gamma t and gamma t plus h on the curve gamma. We investigate its limit as h approaches 0. In case gamma dash t exists, it is called the tangent to the curve gamma at the point gamma t. Now, gamma t is a point in Rm. If gamma dash t exists, it will be another point in Rm. If gamma has components gamma 1, gamma 2 up to gamma m, then gamma dash will also have the components gamma 1 dash, gamma 2 dash up to gamma m dash. So, once we know gamma, we can find out the tangent at the point t. In case gamma dash t is different from 0, we can find the unit tangent vector at the point gamma t. So, it will be gamma dash t divided by the real number norm of gamma dash t. We denote this by T t. This vector gamma dash t is also known as the velocity of gamma at the point t, and its norm is called the corresponding speed. Obviously, norm of T t is 1 for each t. In case gamma represents a straight line, T t is a constant vector, and hence T dash t is the 0 vector. We shall study this in detail in the paper Differential Geometry. Thus, we have studied scalar fields and vector fields on Rn. We elaborately studied vector valued functions of a single real variable and its elementary applications in differential geometry.